Hi and welcome again to my Physics Online video lecture series. Today's video we're going to be talking about motion with constant acceleration. We can begin by recalling that we've already discussed the definition for acceleration, and we've already discussed the definitions for velocity, position, displacement, all that. So we can write those definitions very quickly here. Acceleration was defined as rate change of velocity. Velocity in turn was defined as rate change in position, that is rate of displacement. And we also have that for constant velocity, so for no acceleration, for constant velocity, the position as a function of time is given by the velocity times the time that's elapsed plus the initial position, and that for a constant acceleration, the velocity is given by a very similar looking equation. Velocity as a function of time becomes v is equal to acceleration times time plus v initial. So these are kind of the ideas that are the background to this little video. What we have now is what would happen if we have constant acceleration, but we want to know what position versus time is doing. So what about position? And the way that we can go about figuring out the position versus time is to note that this equation here can be rewritten just using the definition for average velocity, that the position must be given by the average velocity times the time elapsed plus the initial position. So this is just making use of these two equations. And so if we have a constant acceleration, if acceleration is constant, then it follows that the average velocity can be found by taking the final velocity, v final, and adding it to the initial velocity, v initial, and dividing the whole thing by 2. This only works if the acceleration is constant, by the way. If the acceleration is not constant, then this equation is actually not true. This equation right here is true regardless. So this is true regardless. All right. And again, we note that these right here could be given the subscript f for final. So basically, that means that my position should be given by v final plus v initial divided by 2 times time plus the x initial. So that's just taking this equation here and substituting into this equation for the average velocity. And now we substitute for v final, and what we have is acceleration times time plus v initial all over 2 plus another v initial. Okay, so this right here is my v final, this right here is my v initial. All of that's times time, and then I have plus x initial. So if we combine our like terms, what we end up getting is x, the position, is a over 2 times time times another time. So that's 1/2 times acceleration times time squared. We have v initial plus v initial, that's 2v initial divided by 2. So that leaves me with 1v initial times time plus x initial. And this is the equation that describes position versus time for constant acceleration. Note that there are two initial conditions that have been specified here, the initial velocity and the initial position. I suppose in some sense you could say there are three. If we consider that the acceleration is constant, then this acceleration is also an initial acceleration. Is it possible to have changing acceleration? Yes. So this equation is not valid for all motion types. It's only valid if the acceleration is constant or can be approximated as constant. There is such a thing as change in acceleration. It's called jerk. So if you hear the word jerking around, it just basically means the thing has a changing acceleration. And there are changes in jerk. There's jounce, and then the next three changes in are called snap, crackle, and pop, and so on. But for this, for an algebra-based course, we kind of limit ourselves for now to the assumption that acceleration is either constant or approximatable as constant or quasi-constant, which essentially means it's constant over an interval and then it may change for a different interval, but it's constant over that new interval at some other value. All right, let's do an example of this equation. You have a car that's accelerating from rest for 3 seconds. And it does so at a steady rate of 1.6 meters per second squared. We want to know how far the car is going to travel. So in some sense, it's useful to kind of identify what information is being given to us in this problem. So it's doing this for 3 seconds. That would be your time or your delta time. You're told that it is a rate. This is the rate change of velocity. In other words, this is the acceleration. So this is your acceleration value, at least the magnitude of it. Finally, you're told that it is from rest. From rest means the initial velocity is the velocity of whatever you'd call at rest, which generally speaking means 0 meters per second. So we want to know how far it travels. This is the scalar version of this equation. You'd use 1/2 at squared plus v initial t plus x initial, although x initial kind of gets lumped over here into a delta x. So the how far does it travel? How far does it travel? This is a delta x term. Delta x becomes 1/2 at squared plus v initial t. So if we plug the numbers in, delta x is half of, and then our acceleration was 1.6 meters per second squared. Our time is 3 seconds. We have to square it. And then from rest was our 0 meters per second initial velocity. So it doesn't really matter how much time since we're multiplying by 0, but let's for consistently plug in the 3 seconds here. Okay, this comes out to 7.2 meters. So x is about 7.2 meters. And that's how far this thing has traveled. This car has traveled in the first 3 seconds. There is another equation that goes with motion with a constant acceleration. This equation basically is an equation in which we want to put everything in terms of not knowing time. And usually we do this as a scalar. This equation here is shown in vector form. It could be given in scalar form as well. This equation generally, when we remove time, generally is in a scalar form. It could be in vector form using dot products, but that's a little more beyond the scope of today's lecture. What this one is that 2 times the magnitude of the acceleration times the distance traveled, which could be like a delta x or an x final minus an x initial or what have you, is equal to the difference in squares between the final velocity and the initial velocity. So this is another equation that's valid only if you have constant acceleration. Okay, this is useful if you're given an initial and a final, let's say, velocity, and you know what the acceleration is, and you want to know how far the thing has traveled, and you don't want to have to go solving for time first. This comes from basically using this equation for velocity versus time and this equation for position versus time, and substituting the velocity into this equation. Really, it solves for time and substitutes for the time in this equation to eliminate time. And that will result in this equation here, where delta x, recall, is final minus initial. So those are kind of the relevant equations for 1D motion with constant acceleration. Now we can apply it to a variety of problems, but that would be getting a bit outside the scope of a single short video. I will, however, give maybe one quick example here. Right, so we have a motorcycle traveling at 20 meters per second. This right here is kind of our initial velocity, so v initial. The cyclist accelerates by 2 meters per second squared, so this is your acceleration for 100 meters. This is your distance traveled. What is the motorcycle's speed after doing this? Well, this right here would be identified as the v final. So we want to use this equation that says 2a delta x is v final squared minus v initial squared. But we're trying to solve for v final, so we're going to have to rearrange the equation. Okay, so v final squared is therefore 2a delta x minus v initial squared. All right, or in other words, v final is the square root of 2 times acceleration times distance minus v initial squared. All right, so if I'm going to plug numbers in, I have 2 times the acceleration, which was 2.0 meters per second squared, times the distance, which is 100 meters. Oops, I should have added v initial to both sides here. So plus v initial, which was 20 meters per second squared. All right, well, this is 400, and this right here also is 400. So I have v final is the square root of 800 meters squared per second squared. That should, I believe, be about 28 meters per second. Well, my calculator says 28.28. So that's it. Thanks for watching.